Hello friends, welcome to this new video of the series where we are learning how to backpropagate gradient of losses through fully corrected layers and softmax layer. So in the last video, we talked about how we can backpropagate our loss with respect to any of the inputs that we have for the softmax. And for that, we deduced, we found that if we focus on, say, one particular type of loss, say categorical cross entropy, and we have kind of this kind of input coming out from softmax, and this is the actual true values of the classes, true value of the output. Then how do we calculate the categorical cross entropy loss? And then how did we backpropagate this loss with respect to the input of the softmax? And how did we calculate the full loss? And then how did we differentiated this loss with respect to each of the input variables to the softmax layer? Now, coming back to this tutorial, what we are going to do is that we are going to write a very simple classification layer that will have one fully connected layer, and there would be a softmax layer. And we will try to feed some data that we will try to fabricate using NumPy library, and then we will try to optimize the random weights that we generate for, say, fully connected layer, and we will try to optimize those weights and bias to reach to optimized value of these weights so that we can do this classification better. Now let's switch to our Jupyter notebook, and here what we are going to do is that we would quickly import our NumPy library, and then the next library that would be useful would be to visualize this data, whatever we are going to generate as input. So let's try to bring up a very famous library that's matplotlib, and then our famous sklearn. And from sklearn, let's find out the data sets library, and let's import something that can quickly give me some toy data set to play with. Sorry, so this is matplotlib. Now, out of this, what we can do is that we can try to fabricate some data. So what we can do is that we can quickly go and call this make moons, and let's look at what make moons gives us. So if I say make moons, then it expects some kind of input from me. So it will say how many samples we want to generate, and out of these samples, we will just try to make it kind of realistic looking data. So we need to introduce some kind of a noise into this, and let's try to put some noise as little noise, not too much. So say 0.15, and then let's try to give some random state to this so that you run this notebook at multiple locations, and you end up with same kind of result. Now, okay, you need to provide this number of samples. Let's test it with 10 samples, and what's going to do is that it's going to give me one set of two-dimensional points. So this point, if you try to plot this on a two-dimensional plot, then this is the coordinate of one of the points, and then it just assigns one of the targets. It says that this falls into two classes. These classes are going to be either 0 or 1. So each point is being categorized as either 0 and 1. And now let's come back and let's try to generate it for some more samples. So my number of samples is going to be, let's say, 400. And I'm going to, because this is going to give me a tuple, that's why I'm going to assign this to x and y, where x is going to be input and y is going to be my output. And if I try to visualize this, then if I just take just 10 points from each of the outputs, then this is how it looks like. So you have this, sorry, so you need to take white. So now since we have this data, what we need to do is that we need to, uh, so let's, before going to further discussion, let's try to plot this and try to see that how this make moons is giving me this kind of data. So let me quickly plot it. So I'm going to take all the values from the first dimension and plot it against the values of the second dimension. And let's try to give it some kind of C map, color map. So plot has got lots of color maps. Let's try to grab something that makes this graph looks good. So I choose one visualization, and that gives me something like this. Well, okay, I need to change the number of samples. So I generated 400 points. So you see that I got this kind of data. Now I want to see that in which classes they are falling, because make moons is something that gives you two categories. So let me give colors to each one of them. So if I just use the values in y as my color map, then it's just going to show me exactly that in which category these two data sets are falling into. So all the red dots are going to be in one class, and these blue dots are going to be into different class. Now, what we are going to do is that we will try to classify them. So because this data is kind of quite close to each other, and drawing any boundaries so that we can clearly demarcate these domains, these classes, is going to be difficult. So let's try to create a softmax layer. So I will go and simply try and create a softmax single layer classifier. And by single layer, I mean that I'm just going to place one fully connected layer between the input and then a softmax layer and then definitely the output. So when we define the dimensions, my dimension is going to be 2. That's why we have generated using this make moons data sets. And now number of classes is going to be 2 because as you see we have blue and red. So these are 2 classes. Now let's try to create a connected fully connected layer. And for that, I need a set of weight, and that weight dimension is going to be using this value d and k. So I'm going to use numpy random library, and this is going to give me a set of weights. So I'm going to give dimensionality as d, and then the number of classes is going to be k. Now the bias is going to be, again, we will use numpy library, and we start with only zeros. So this is going to be a one-dimensional vector that is just going to mimic only the second dimension, that is k. Now let's go and do the actual operation. Now we are done with our weights. So if you try to see how the weight looks like, then you can just grab a bunch of values and see that this is how your weight is going to look like. And now these are the values of the weights that we would like to optimize. And now let's go to the actual calculation. So the first step that happens is that we try to take a dot product, and that's how it happens when we try to feed any input to our weights. Then we actually take the dot product between x and w, and then we add the bias. So let's call this expression as one of the variables. So we assign this to score. And now it will go to the softmax layer. And in softmax layer, what we do is that we first do the exponents of this score. So let's define another variable and try to take exponents of this score. So simply write this expression, and that's going to take exponents of each of the scores in your score. That's the dot product between input and the weights. Now, the next step is that if you remember from the last slide that we just discussed, that we have to calculate this probs, or what we call as output of the softmax. And what we do is that we divide each of the exponents with the sum of all the exponents for one of the classes. So what we need to do is that we need to take this exponent score and we need to divide it by sum of all the values that we have in one of the classes. Now, the axis that defines the class is going to be 1, because I'm talking about just one row. So if you have one output that corresponds to one of the rows, and that rows will have either zeros and 1, and we will have a number of predictions, and we try to normalize this along the axis 1, and that will give me the output of the softmax. Now, I would like to keep the dimensions as same because that is something that will help me to calculate the losses. Now, next step is, if you remember from the last slide that we looked upon, that was we were taking the negative log of all these props values. So we will again define one more variable, and what we are going to do is that we are going to take negative log of these props, and um, what the only values I'm going to take negative log is the ones for which we have the label true labels as 1, and not for them that is 0. So I will resort to all the values that I have in my input. So I have n number of samples. So I will go to each one of the samples, and I will only select those one that has got some true values as 1. So I'll rely on y, because y is going to give me the actual output that we just fabricated using random numpy random values. So this is what we did. So now this is the step where we have ended up doing lots of that. And now this is going to help us to give me the loss, because all of the terms of this log props, we are just going to take sum of that. So we just say, okay, log props, and this is my final loss. So if I go back to my earlier section, so you see that this is how we were doing. So uh, finally, we were taking logs of only those terms for which we were having the value as 1. So this is my true label. This is my true label. And this is how I was trying to take the probability. So this is the step that I just did in the code. Now, coming back to that, once we do have this loss, then we always end up with exploding gradients, because my loss is going to be quite high. So I need to add some more parameters so that I can add some regularization to this loss. So let us add some parameters. So I would add a parameter that will be regularizer. Let's take some values at 1 exponent minus 3, and I also need a learning rate because every time I apply the gradients, I need to use this value to multiply it to the gradient and then add it to the values. So now let's try to find out the regularization loss. So we will have to add this regularization loss. So we'll call it reg loss, and that would be equal to the standard formula is half then regularization coefficient, and then you need to take the sum of the square of the weights. So we do this expression, and then we add this reg loss to overall loss. So what we end up is that we have our final loss as adding this reg loss into that. Now, if we need to convert this back propagation, this gradient, so that's why we need to reduce down this loss value by dividing it by the total number of samples. And then we go for back propagation. So now here comes the back propagation, and here we will apply all the chain rule of differentiation that we just learned in the last lecture. So we saw that when we have to take gradients of the loss with respect to the weights, then we use the input, transpose of the input, and we multiply it with my dou L by dou score. So let us try to create one term called d score and give it value props, because props is the output of softmax layer, and I would be interested to back propagate this loss through the softmax layer. And from our earlier discussion, we ended up with one expression, and that expression was kind of quite simple, where we just used what we did here. So we ended with one of the expressions saying this, and for that we just had to actually reduce one from that. So we ended up with a very simple looking expression when we had to backpropagate this gradient to the softmax. And that is the thing that we are going to do. So we are going to take the props, and we are just going to reduce a value that is -1 from that. So now here, coming back, let's take this d score, that is props, and if I have to take the gradient, I mean backpropagate the gradient through this props, the only thing that I need to do is that I just need to deduct 1 from this. Now I do not need to do it for all the values in the matrix. I only need to do for values that has got the true label as 1. So again, I will apply the same logic here by using the same thing. So let me take this indices. Now quickly only touch upon those indices and reduce -1, reduce 1 from those values. Now my D score is kind of simple, and again I will normalize it a little bit by defining this again by the number of samples so that I can get rid of this exploding gradients. Now let's backpropagate the gradients. Now how do we backpropagate the gradients is by then going to the fully connected layer. And when we go to the fully connected layer, we have all the weights. And now if we take dw, then from our earlier discussion, we just have to actually multiply the transpose of the input with the d score value. So what we can do is that we can just take a dot product between x dot t and the d score. Okay, so and if we try to understand that what this is, then this is just following the chain rule. So what we are interested to find out is what is this d loss divided by what is the gradient of loss with respect to the weight, and that's what is signified by dw. And this is coming out of two multiplication. The first multiplication is the x transpose, and then the d score. Now d score is what we call as d loss, and divided by d score. So what we are trying to do is that we are first trying to differentiate the loss with respect to this parameter, and then we are going to differentiate this score with respect to dw. It means that we are going to differentiate this expression with respect to this capital W, that's the weight of the fully connected layer. So finally, when we multiply these two things together, then what we end up is what we know as d loss by dw. So this is basically d score divided by dw, and that's what is being done in this expression. Now, same way, what we can try to find out what is the gradient with respect to bias, and that is a simple one, because if you go back to this expression and we try to differentiate this expression with respect to b, then this is just going to be 1. So this would be simply equal to d score, but to match the dimension, I mean, we can just write it as d score, okay? But this dimension is not going to match it because db is just single vector and d score is a matrix. So we're going to reduce this. We are going to take NP sum, and we have to decide what kind of axis. We need to take the sum, and that axis is going to be 0. Now we can quickly go and apply these gradients And when we apply these gradients, then what we need to do is that we have to add um, we need to use this dw and db when we have to apply these gradients to gradient. What we need to do is that we need to use the learning rate and multiply it with this dw. And the same way, what we can do is for the bias, and we can use the learning rate here, and we can use db. Now so this is the whole calculation. Now this is just one iteration, and what we need to do is that we need to repeat it multiple times. So we need to define some kind of iterator. So now let's try to put it into a loop. So for epoch in range, how many iterations do we want to do? So let's stick to 10,000. That should be pretty enough for these kind of weights to be optimized for this kind of classification. Now for each time when there is an iteration, we would like to see that whether the loss is going down or going up. So let's try to print all these values. So epoch in sorry, let's try. So whenever this epoch modulus 1,000, it means that every 1,000 times, every 1,000 iteration, I'm going to print the value. So let me print this iteration as decimal, and let's print the loss as loss as a fraction. So just let's call it as f, and then let's provide it these two values, so epoch and the last. And now when we do that, sorry, a little bit of errors. So for okay, now this is going to converge. So you see that the loss started with a high value, then it's going down further on. It's not changing any later. Now we can assume that because this loss has now converged to a pretty low value, then it must have certainly converged to this thing. Now coming back, now let's try to now see whether this classification is working or not. So now somehow we need to use this weights, whatever optimized weight we have actually ended up with. We need to first evaluate this model. So let us try to first of all see that whether these things are good or these things are bad. So let me try to use these weights. For that, let me try to write a function that will use these weights. So I'll create a predicate function that will take some kind of input, and this input will be similar to what we just fabricated. So we are just going to use the same data set, what we fabricated, and then we will see that if we use these weights, whether this is going to give me the actual value y or not. So let's try to repeat this calculation, because every time we try to feed any input, then these are three steps that gets executed. So we can just copy this thing and we can place it in. And then the only change that I'm going to do is that because this is x, so we're just going to replace this with x in, because that's something that we are going to feed it with. And finally, this is going to return me probs, and that prob, as I said, that for each of the classes, this will be normalized softmax score. So for each of the categories, it's going to give me the probability. So I'm going to take the one that has got the highest probability. So I need to define axis as one, and then I need to take the argmax. So whichever value is going to be maximum for one of the classes, I'm just going to take from props. And in order to do that, in order to pick that from for horizontally for one of the classes, I need to set axis as one. So this function is just going to take my input. So let us test it with my x, and not all the values of x, but let's take values 1 to 10. So if I take first 10 values, then it is for the first one, it's going to give class as 0. For the next one, it's going to give as 1, and so far and so on. And let's try to quickly see that what is my accuracy of the model. So let me try to write another function that will evaluate this model. And for that, the input that I will be requiring is all the predicted value that will be coming out from this predict one layer function if I feed all the values as input. And I will try to compare it with true values. So these are the two inputs that this function will need. And then let me quickly assert whether the shape of these two things are good or not, because it's possible that we might give just a chunk of values and the shape doesn't match up. So all the prediction will fail. So let me do this small step. If not, then let me write one comment: shape of the inputs should match. Okay, that's it. And let me then try to calculate a variable that will be called accuracy. And for that, what we need to do is that we need to sum all the values where my y true value is going to be equal to my y pred. And I will just divide it by my y pred to get me the percentage score. So however, this the value of the shape, we take the first index, and then let me just print this, saying this is going to be my accuracy. So I will say accuracy of the model is going to be, let's write a fraction. So dot 2f and then provide this value as accuracy. Now, if I have to evaluate this, then I will just call this evaluate function, and I will give the actual values, that is the true value, and then I can give my predict one layer, maybe this way. Sorry, yeah, prediction, and then the true value. And the prediction, what I'm going to do is that I'm just going to do this. So now the accuracy of the model that is says is 84%. That's fair enough. And let's try to now visualize on my data that whether this classification has worked or not. So in order to do that, what I'm going to do is that, first of all, let me try to generate a random set of points, and that will cover all of my area. Then I will try to use some of the functions that can highlight different sections of this category, these classes. So, okay, let me try to generate a mesh. And in order to generate the mesh that will go and sit on top of this scatter plot, that let's just take 10 points, and I will generate two sets of value by trying to use the mesh grid. So I will explain that what mesh grid does, but before that, let me give a range of values. So mesh grid generates a grid of values for a given ranges that you provide. So it takes two arguments, two ranges. So let me give one range, and that range will be created by linspace function. And linspace function is a function that takes two sets of values, and then it gives you a number of points between the minimum and maximum value that you provide. So let me give the minimum value as coming from the first dimension of x, that is the input. So we can call it as the x-axis or something, and take minimum of that. So I'm taking the minimum of the x-axis, and then I'm giving the maximum of the x-axis. So I'm taking these two values, and between them, I would ask the mesh grid to give me n points that equal to 10 right now. Now let me cover a little more area, so I'm just going to reduce 0.5 so that it covers kind of full range. So and I add 0.5 similarly to my maximum. Now it will also give, it will also expect another input, that is the y-axis. So I'm going to use the same thing. The only thing that I'm going to do is that I'm just going to change the dimension, the axis. So for the second argument, I'm just going to change this 0 to 1. So now this is taking the second dimension of the input, that's y. Now, if we look at how xx looks like, so the shape is going to be 10, 10, and yy dot shape is also going to be 10, 10. And how it's going to be useful is that we can just stack these values. So first of all, I need to convert this xx because there's two dimension. Let me convert it to one dimension. And if you do that, then that becomes one dimension. So all these 10, 10 values is converted, is flattened as 100 values. And similarly, what we are going to do with y. And based on these two sets, what I'm going to generate is a two-dimensional value. So I'm going to concatenate. It means I want to actually keep these two sets of values side by side. So I give first input as this and second input as this. And finally, you see that this gives me a two-dimensional input, similarly like what we generated for my x and y earlier in this topic. So once we do that, let me quickly try to give some sense of it. If I just go to plot and I try to scatter this and say, if I take just 100 values from here, so let me take 100, and let me take 100 values from here, and let me just try to plot this. So scatter, and okay, so I need to, sorry, so only required positional argument is this, and PC, okay, that's right. So what I'm going to do is that I'm just going to take these two values, and let me just give you a glimpse at how does it look like. So now this is the mesh grid that I was talking about. So I'm just taking 100 values out of this, and this is trying to cover the whole of the area. And let me try to actually give some color to this. So let me take range 100. So that's how you see that each one point is now taking the color. So each point is having a different color than the earlier. So now if I use these points and send it to my predict layer, then that is going to categorize it as either at 0 and 1. So now what I'm going to do is that I'm quickly going to calculate my another variable that is going to use this mesh grid values. And then I'm going to superimpose this categorization on top of my earlier original scatter plot. So let me call my predict1 layer, and this predict1 layer is going to take an input that is similar to x. That's why I want to concatenate these things, and for that I'm going to ravel it, and raveling means that I'm going to flatten this xx that is 10 by 10 and making it just a vector having 100 values. Same for y, and now we can have this 100 by 2 values that is similar to x. And when we do that, then this z, sorry, so okay, this is npc, Oh, sorry, this is like this. So now if I check the shape of this thing, then this is going to be 100. So 100 values for all of this, and you can also check the values here. So it's either 1 or 0. Now, let's try to, now this is one dimension. So we just want to actually, because we are going to use a function that is contour f that is going to take the first grid points and second grid points and then take z. But it's not going to give you right value because now z is having a different dimension. We need to convert it into two dimensions. So let me reshape it. And let's the first dimension is -1 because it's going to just use second dimension to calculate that. Now you see that I am getting two different categories. So earlier, if you remember that we did a scatter plot for xx, so I'm going to do it once more. So let me take first 100 values from here, and then from y, I'm going to take 100 value from here, and let me see that how does it look like. And this is the mesh grid, and we also gave it color. So each one of the inputs is going to be different. So if I try to number them, then color them, then that's how it is looking like. And for each of the values, so if I focus on this particular point here, then this is going to be categorized as 1, then this 1 is going to be colored as purple. And similarly, if I look at this point, then this is going to be categorized by this train softmax layer as something else as 0, and 0 will have a different color. Now what we can do is that we can just superimpose the earlier scatter plot that we did with our actual inputs. So let's take all the values from dimension 0 as x-axis and all the values from dimension 1. And let's try to superimpose that. And that you see that these are, okay, now let me try to also change the CMAP. So from the plot, I'm going to get my CMAP, a convenient CMAP. Let me go with a very simple binary. And here you see, okay, should work. Plot the C, sorry, I did not, I forgot this. So C is equal to Y. Now you see that you have two categories. I have tried to actually give different colors to different classes. Now you see there is a clear boundary between this white and gray, but this is still not clear demarcation, still not clear classification because these points are kind of quite convoluted. They are actually getting into each other. So we need to draw a very clear boundary so that all these black boxes should actually fall into this yellow area and all the white points should fall into blue. And for that, I need to make some changes to my model, and that's what we are going to do in the next video. We're going to just go and add a few more layers to a model and retrain the model so that this classification is going to be proper. So thanks for watching for this video. Wait for another video where I'm just going to give a facelift to this model and add one more layer so that it does the classification much better than what it is doing. Thank you.